So we start the colloquium this month. I asked Professor Ralph Willox of our graduate school to be the chairman today.
Thank you very much. It is a great pleasure to welcome our colloquium speaker for this month, Professor John Roberts from the University of New South Wales in Sydney. Professor Roberts is actually visiting the graduate school for 3 months. 3 months that have almost elapsed. There's about 2 weeks left, 2 weeks and a day, I think. Personally, I feel the visit has been very productive. I hope that feeling is mutual. Professor Roberts, I think many of you know of his work. I can say he's one of the pioneers of discrete or research in integrable systems in the discrete realm. Not only mappings, because today's talk will be about maps mainly, but also on discrete lattice equations, and I think it's fair to say that you're also very interested in all of the ramifications of research in integrable systems, discrete integrable systems, into other fields, other parts of mathematics. So there will be I don't think there will be a lot of number theory today, but next week in Kobe there will be connections to number theory, but there will be aspects of arithmetics and geometry in today's talk, and I'm looking forward to the talk, so please start.
Thank you very much. Thank you for the invitation for the colloquium, and I must also thank Ralph, Professor Willox, and the school for the scheme that's allowed me to visit. It's a wonderful scheme, if I may say so myself, and I feel very fortunate to have had some time here, and I think there are lots of interesting ideas floating around that we'll be able to pursue. But I'd like to thank the school and Ralph in particular for wonderful hospitality. So as Ralph said, I like very much to see dynamical systems and integrable dynamical systems as wonderful umbrellas in order to wander around and see different parts of mathematics. And today I'm actually not really going to be talking about integrable dynamics. I'm going to be talking about just nonlinear dynamics. It does have some overlap. And this is based on ongoing work. There's already 2 papers with Asaki Sato from the Future University in Hakodate and Franco Vivaldi in London. But this is a colloquium, and my understanding of a colloquium is you're allowed to go a little bit wider than specifics. So I'm going to take this opportunity to eventually explain some of the work that we've done, but I again want to emphasize that many different fields meet here, which makes it a lot of fun, and it makes research a chance to learn something, or self-learning, which I think is very important. And so I'll take a detour to outline connections with various areas of maths and physics, including some that I realize I worked on 30 years ago, which is a little bit confronting. But I like to often start a talk that's dealing with dynamics by emphasizing the power of a toy model. And so my dash here is my image point, and this is the famous area preserving map of Michel Hénon. And he had a wonderful ability to make maps of the plane that contained the essence of phenomena that, in this case, were associated with Hamiltonian dynamics. And of course, most of you will know the non-area preserving version of this that has the famous strange attractor. Okay, so it's about as simple as you could get. for nonlinearity. It's polynomial with just a square term in it. And the beauty of it is that its phase portrait shows all the features of general non-integrable Hamiltonian dynamics. In other words, we see genuine invariant curves. So this is a computer plot made by taking many initial points and just iterating with the computer. So we see invariant curves, invariant islands, which are just sort of around periodic orbits. But then we also see orbits that just produce a chaotic sea, like the aqua-coloured orbit. And of course, even though this looks like a fairly rigid picture here, it's not a fibration by invariant curves at all. If you blow it up, you get this incredible interlacing of chaotic dynamics and motion on invariant curves, quasi-periodic rotation on invariant curves. And so the fact that we see this is a manifestation of KM theory. And so in red there, I just have a map in polar coordinates. R dash equals R, so it's a map that preserves circles. And that's the picture on the top right. On each circle, there is, the angle is advanced via a rotation where the angle depends on the radius of the circle. And the reason I'm doing this is because actually this is going to dominate the talk. It's largely about rotation and the connection with the number theoretic nature of the angle, irrational angle that you rotate by. Because obviously if I had a rational angle, like 2/3 of one revolution, I'm going to come back to myself after 3 iterations, and every point on that curve will be period 3. But if I have an irrational, then I can densely fill the circle with a quasi-periodic sort of rotation. Okay. So this is a way of getting this type of complicated dynamics simply by taking one map that is nonlinear. But even so, and this is another point, such simple maps, there's still lots that we don't know about such simple maps. For instance, the measure of the part that is regular in the plane. But the other thing I want to emphasize is the importance that this work, which was largely sort of done by the particle accelerator physics community, already showed that how irrational this number omega was played a big part in the robustness of this curve to perturbation. So the KM theory is really a theory that says when you take that red map, the twist map, and then you add perturbations to it so that you still maintain area preservation, then you break up the whole curve of periodic orbits will break up just usually into a family of 2, a hyperbolic and an elliptic, but you will retain some invariant curves, and that's the amazing result of KM theory. So that means that near to integrable still retains some of the features of integrable. But if you're perturbing and the curves start to break up, the order in which they break up has a lot to do with how irrational the rotation number is. And things like 1 on the golden ratio like here, whose continued fraction expansion ends in ones, or is all ones, they will be the sort of most robust curve to break up. Okay, but we want to try and make some non-trivial dynamics without having to go non-linear. Because of course, in our courses, in linear algebra, sometimes we might tell our students, well, you know, what is the geometry of just multiplying a vector by a matrix? And if I'm going to insist that the determinant is 1, then, you know, Jordan forms will tell you that, you know, generically you're going to, the motion of the map is going to live on arms of hyperbole, or if you have eigenvalues that are complex conjugate on the unit circle, then you're going to preserve basically a family of ellipses. Okay, how can you make something a bit more exotic? Well, that's what we want to talk about. And another way of introducing complexity is to go piecewise linear. So this is a map that was introduced by Jeffrey Ligarius and Eric Rains. I'll give some references at the end. They basically published 3 papers on this in 2005, but apparently they did the work in the 90s as part of their extra work when they were both employees of, well, Bell Labs or IBM. I can't quite remember. But anyway, the idea is this. I'm going to have a piecewise linear map, and the boundary is the y-axis. And if a point is on the right-hand side, I'm going to apply this to my starting vector. And if it's on the left-hand side, I'm going to apply this. So there are 2 parameters in the problem, which are the traces of these 2 matrices. And it's continuous map because you'll notice that the y-axis is sent to the same vector by both. So the idea is you choose an initial point, and if you like, it makes sense to connect it to the origin and think about a ray. And you, if this is your x0, y0, you keep on applying this matrix until some point you land over here, and then you apply that, and you just keep on building the dynamics this way. Now, along the way, I want to code what's happening here. And, well, it's a little bit clumsy, and I don't have many fonts to work with. But basically, I'm going to code it again with A, but I don't mean the value of the parameter. You know, so if I took an initial condition and the first 2 iterates were in the right-hand side, and then I had 3 iterates on the left-hand side, I'd go this. So in other words, what I'm doing is I'm building a symbolic dynamics for my orbits. And you can ask yourself questions like, for what values of A and B will I have bounded dynamics? Yeah, which is the big question in physics often. And the other thing that's nice about piecewise linear is that you know, rays through the origin are going to map to rays. So this means that every time I know where this goes to, say over here, then I know that anything along that ray, you know, if this is just lambda times my initial vector, then it'll be sent to lambda times the image vector. So that's an advantage that I can exploit, and it means that once I know the orbit of one ray, I get the orbits of all its multiples. From a point of view of integrability, say, this is interesting because it means that if we wanted to call this integrable, notice this is an area-preserving map because each of these is determinant 1. So what this means is if there was an invariant curve here, and I could really prove that this was an invariant curve, then by this scaling argument, the whole plane is just foliated by scaled versions of this curve. So in terms of, if you want to think about integrability, the question now is there one compact curve? Okay. But here's where I want to take a bit of a detour, because you'll see what I wrote here, that at time t, where you are can be considered now as a matrix word acting on your initial state. So I said that here I was going to put symbols that would tell me if I was on the right half plane or the left half plane, but the action of the dynamics is, I'm just acting a matrix, and let's call that capital A, if it's on the right half plane, and a matrix on the left half plane. So I can say that what I'm really doing is building a matrix word, and the only difference is that I write this back to front, if you like. So this would be, I took x naught, y naught, then I applied a squared, b cubed, sorry, and then a, etc. Okay, is this all right so far? Okay. All right. Okay. So already there's some nice things going on here. There are 2 by 2 matrices in SL2Z, and there's words being built. So there's a combinatorics aspect to this. And so the detour I want to take is to talk a little bit about other examples of this. So you could argue that what is happening here is that this word is being built by the dynamics. And in a sense, I have to do the dynamics to make this word. It turns out that's not exactly what's happening here because of the number theoretic nature of the word. But let's contrast that with something else. And that is something that is seen in mathematical physics and is a big area of research, and I'll say a little bit more in a moment. The discrete Schrödinger equation on a one-dimensional lattice turns into doing exactly the same thing with 2 matrices, and you build a matrix word which is given to you by a sequence of potentials that you lay down on a lattice, and they will choose the word for you. Okay, so on the face of it, they look to be the different things. This one, you have to do the dynamics to get the word. This one's prescribed. Of course, if I now look at just ratios of variables, then what I'm really doing is studying transformation semigroups where the transformation are Mobius transformations. And there's a lot of nice mathematics, a lot of nice articles by Bldg, for instance, on what is the eventual dynamics of words that are made up of from a family of Mobius transformations. And all of this often leads to studying things that are like continued fractions, but they're actually functions. They're not continued fractions in numbers. So let me say a little bit more about these so-called trace maps. So the starting point is this second-order difference equation, okay? Linear difference equation, so easy as can be on the face of it. And the idea is that I imagine I'm on a one-dimensional lattice, and I'm going to tell you a potential sequence to put at the sites where you can choose between two letters, two values, V0 and V1. And the problem is to propagate this equation via this transfer matrix. So this is the transfer matrix that tells you how to build, if you like, the wave function moving from one site to the next. And you see the matrix is exactly of the same type as we have here, where my value A is just, say, E minus V0, and there's going to be a value B, which is E minus V1. And so this is an example of what's called the diagonal tight binding model of the one-dimensional Schrödinger equation. It looks simple, but it's received an amazing amount of research since the 1980s, particularly since the discovery of quasicrystals, which made people want to put in quasi-periodic potential sequences on the line. So the general problem is this. Given the sequence, what values of E, the energy, are going to give bounded solutions for all n? Now, it turns out you can turn this via the nice algebra that's involved here into an equivalent dynamical problem. Associated with this, you can build a polynomial automorphism of R3 or C3, which is commonly called a trace map. And it has the initial condition, well, the physicists always divide the trace by 2, which actually means that sometimes I'm writing down things that in the mathematics have slightly different exponent, particularly on this term. But anyway, you'll notice that this is the trace of the first matrix, this is the trace of the second matrix, and this is the trace of the product of the two matrices that I could have. And it will turn out that this trace map has an invariant, which is often called the Fricker-Vogt invariant, because the mathematics of this goes back to Fricker in the late 1800s. So we're going to have a polynomial map, and it preserves this quantity of x, y, and z. And if you take that initial condition, it shows that you're living on a level set of this where the height is always positive. So here's a picture of some level sets of this. So for, if mu is positive, it consists of this shape with 4 trumpets coming off, okay? And then as you take mu backwards to 0, the inner part becomes a sort of a tetrahedron, and then you have 4 points with cones attached to them. So it's like a sphere with 4 punctures. And then if you take mu negative between 0 and -1, you get the 4 sort of cones, and you get a little ball which shrinks to the origin at -1. and then beyond that you just have the 4 trumpets. So suppose I build a sequence of potentials which is based on the Fibonacci numbers. And so this is called the Fibonacci word, this semi-infinite word. You notice that if I track it along the Fibonacci numbers, the ratio of V0s to V1s is 2/3. And then if I go up to 8, I'll find it's 3/5, and so on. And so that's why this is called the Fibonacci sequence. There's many ways you can make this sequence. One way is to use this 2-letter substitution rule, which says I'm going to start with a seed, and then I'm going to make it longer. Wherever I see V0, I'm going to replace it by V1. Wherever I see V1, I'm going to replace it by V1, V0. And then you see that if you started with V1, you'd grow it to V1, V0. And then the next iteration, this V1 would be V1, V0, and the V0 would go to the right, be V1. So you can grow it by this so-called 2-letter substitution rule. And here is the mapping, the polynomial map of 3 series, which you can check preserves this integral. So the thing that's happening here is that the motion of the wave function is a product of transfer matrices, and you're really asking for what values of E will you have bounded trace of this transfer matrix as it grows. That's why it's a trace map. So the question you really have to ask yourself is, what's the trace of a word in these 2 possible matrices in SL2C? Okay, and one thing you do know is that once you tell me the initial condition, it will be set for all time what surface you're living on. And this particular physics problem will have you living on the positive level sets of this. And I'll mention in a minute, there are other problems that have you living on different level sets. Okay. So it turns out that therefore studying the dynamics on these level sets of this polynomial map, and in particular asking what are the non-escaping points as you take n to infinity from iterating this map. And so a long time ago, I looked at this and I came up with an escape criteria, which was a zone on one of the necks of the problem, where if you were going to escape, you had to enter there. And if you did enter there, you would effectively go off super exponentially. And so really what you wanted to do to find the spectrum was to calculate the pre-image of that particular condition, because your initial condition, if you like, is a line parametrized by E that's lying on this level set. So you want to pick off what is left of this line. Okay, so that approach and various other approaches which identified that the dynamics of these trace maps on this surface was near hyperbolic type dynamics, can be used to show that the energy spectrum of many of these one-dimensional Hamiltonian Schrödinger operators with quasi-periodic potentials is a Cantor set of zero Lebesgue measure. There's a very nice monograph, I'll give some references at the end, by David DeMunnick and Philman on this. And it's also worth saying that the Fields medalist Avila partly got his Fields Medal for some of his work on this. He extended a lot of the results about when you would get the spectrum with Cantor said zero-Lebesgue measure, depending on properties of the dynamically generated potential sequence. Now, I mentioned that there's other problems that map onto this. One of them is the growth of Markov triples. So these are triples of numbers in C3 that satisfies this. Often in the maths literature, the 2 is a 3. That's just an example of the different scalings that people use. And that turns out, that problem has you living on the value of this Fricker invariant with mu equal to -1. But you can also ask escape type questions. And this relates to quasi-Fuchsian groups. That was the interest of Bldg in 1998. But also this is connected to Markov numbers, where you probably know that better, where you look for integers that satisfy this relationship. And you probably know that you can start with 1, 1, 1, and then there's a systematic map you can apply to generate a tree of all the Markov numbers. Okay, so where does all this come from? Well, it comes from the fact that there's a lot of algebra and geometry here which you can exploit. So this is fun if you're teaching linear algebra. Suppose you have two matrices in SL2C. Then the trace of any word in these two matrices can be written as a polynomial with integer coordinates in the trace of the two and the trace of their product. Okay? Which explains why the trace map is in 3 dimensions, because I need the trace of each matrix that's building the word, and I need to have the trace of their product. And you can show this just by recursively playing with Cayley-Hamilton theorem for the two matrices. A very important object is this, the multiplicative commutator of the two matrices. See, if M1 and M2 commuted, you see that this would be the identity, and this trace would be 2. But it turns out that in general, this trace is 4 times that Fricker-Vogt function. In other words, x squared plus y squared plus z squared minus 2xyz minus 1, for me at least, or in the physics literature. And that is equal to 2 plus the determinant of the, what's sometimes called the additive commutator, which is just the difference of the two matrices. And so if the two matrices commute, it means that the matrices are on the 0 level set of this, and it means that these share an eigenvector. And that's going to come in to what we're going to talk about a bit later. And then ultimately, there is a whole lot of work which is very nicely reviewed in various papers by, say, William Goldman. And that is, if you look at the group of orientation-preserving polynomial automorphisms of C3 that preserve this Fricker-Vogt character, it has this very nice semi-direct product structure. And the important part of it is the matrix calligraphic G, and this is just the free group on 2 generators. So there's a lot of beautiful work here, And you can use these generators, and this might look familiar to you because this is the involution that you use to grow Markov triples, Markov numbers. If you've already got one, you can use this and switching around to make the other ones. Okay. So let's come back a bit, and I want to go back towards this piecewise linear map that I started with. But an important part of this dynamics is going to be that there's an underlying circle map. So what's a circle map? A circle map is a homeomorphism of the circle, and I'm going to introduce a symbolic dynamics on it too by, oh yeah, that's not going to work, is it? Okay, where it's okay, I've got it on a slide, so thanks, Phil. Okay. And again, this goes back to the start of dynamical systems. So let's look at a rigid rotation on the circle, where I just choose an angle and I start iterating. And as I've indicated there, I'm going to mark a point on the circle, call it rho. So it breaks the circle into two intervals. And I'm going to give the symbol A if I land in IA, and the symbol B if I land in IB. So in other words, just by looking at the iterates of an initial condition, I will be able to write a sequence of letters, a bit like I've been doing up to now in various ways, and that will be the symbolic dynamics corresponding to this particular rigid rotation. As I said before, right back at the start, obviously if I start with a periodic orbit, if I start with a rational value of theta, I'll have a periodic orbit, and if I start with an irrational number, I'll get an aperiodic orbit that densely fills the circle. Now, an important concept is the language associated with this semi-infinite word that I'm building. So keep on doing this ad infinitum, and then go along the semi-infinite word and look at all the different words that you see of length n. And then this gives you a complexity measure of the word, kappa n, which is the number of words you see, different words you see of length n. If I'm using irrational rotation, then nice ergodic properties tell me that this is independent of the initial condition. And then there's two possible complexities. So the top one, well, let me first say. So a key point here is going to be, have I got a critical orbit? So in other words, I'm going to choose, in my circle map, I have two parameters, theta and rho. And I'm going to ask, is there an orbit that involves zero and rho, the boundaries of my partition? Okay, that's a special type of orbit. And it makes quite a difference to the complexity of the word, because if I call L the transit time between the boundaries of the partition, and I'll take L to be infinity if there is no such critical orbit, then the complexity of the language is 2n. On the other hand, if after some L, the angle I chose is equal to rho mod 1, then L will be finite finite, and I will have a complexity which is n plus L. And the case of Fibonacci, which I talked about, is the simplest case, L equals 1, and so this is a Sturmian word because if you take theta is 1 on the golden ratio, and you take rho equal to 1 minus theta, then you have L equals minus 1. In other words, one iterate backwards in backwards time will bring the 2 points of the partition together. Okay, and indeed, this is how the theory of those Schrödinger equations works. You basically drive the potential sequence via the sampling of a irrational rotation on the circle. And the question is, how is the spectrum decided and what are its features depending on how irrational this, basically how irrational is the angle that you're using. Okay. So we decided, because it didn't seem to have been done, to investigate these things more for circle maps. Okay, so we're going to get to this later, but let's start with a first exercise. Take a circle map. We've got 2 parameters, theta and rho, and we have a parameter space, 2-dimensional parameter space, theta rho, and we're going to say that there's a critical orbit if there's a finite suborbit containing both 0 and rho. So in other words, I wrote it here, there exists an integer L so that some multiple of the angle ends up to the partition variable. And if you want to get rid of the mod, you can say there exists 2 integers so that this relationship is true, which of course is just giving a line in the theta rho parameter space. You can call the part of the orbit between the 2 boundary points of the partition the center, and you can record its symbolic dynamics based on this. It's A if the point lies between 0 and rho, and it's B if it's between rho and 0. You can record that symbolic dynamics. And then you can also say that the word is positive if this is an orbit that's starting at 0 and ending up at rho, or you can say the orbit is negative if it's an orbit that's starting at rho and ending up at 0. Okay, so the general aim of all of this is to understand how these special critical orbits act as the scaffolding for the symbolic dynamics of the critical orbits. Okay? So, and there's a big difference between if your angle is rational or irrational, because if you start with a rational, suppose you start with 3/4, and you ask yourself, what are the possible rows so that this could be a critical orbit? Well, if it's 3/4, the iterates of 3/4 mod 1, there's only going to be 4 of them, so there's only 4 possible rows. One of them is rho equals 1/4, and the way you get to rho equals 1/4 is to take 3 lots of theta, and then your j would be 2. So this defines this line. And so according to what I said above, I would have, this would be my center, which describes how I go from 0 up to rho. And because I don't record the last point, the symbol sequence would be AB squared, because this and this are in the second interval, so they're B's, and I started with 0, which is A. On the other hand, there's an associated negative centre and word, because from 1/4 I go back to 0, and that would be a negative word. Okay. So if you now plot this in parameter space, so this is the parameter space for the rigid rotation, theta rho. And so these are all the possible lines where the slope is bounded by some n. I think it might be 8 here. And obviously, these are important lines because these are the boundaries that decide the symbolic dynamics. So if you cross them, the symbolic dynamics changes. So that's what I mean by sort of a division. This is a little bit like, what we're attempting to do here is a little bit like people do in bifurcation diagrams, where people have parameters and they show the parameter space, and you want to show different areas of the parameter space where you see different phenomena. Okay, so we can understand what the symbolic dynamics is in these regions by referring to the boundaries of the critical lines. However, we can also ask the following question too. As we walk along these critical lines, how does the symbolic dynamics change? And you'll see that you have intersections with these other lines. So as you might expect, it's the intersections that are changing things. So I'm now not going to worry too much about the details, but I'm going to try and talk in pictures because the details are a little bit finicky. But basically what this theorem says is that if you walk along one of these chains, then in a certain range of theta, all you have to worry about is do you find a Fairy number whose denominator is less than or equal to n, which is the absolute value of your slope. And so these Fairy numbers partition the line into different critical curves separated by single points, which we call the Fairy points. And so really, let me just show you an illustration of this. So remember, this is my line. And of course, really, this line is just saying, take rho equals I theta, choose an I, and now just plot this mod 1. So of course, you're going to get I branches. And really, the J is just labeling the branch. Okay? So here's an example where I is 7. And so if I look between 5/7 and 6/7, I will have travelled from 0 up to 1. And I want to walk along this. And this is an illustration of that theorem. So I look at all the denominators that are less than 7 that I see, and I've just made this horizontal, but I'm walking along a slanted line. And I record the symbolic dynamics at my point. And so what happens is you see that as I move along, I change one letter each time. So b to the 7. So I started down here. And so my rho was 0. So everything is above rho. So everything gets the symbol b. So that's why it's b to the 7. And then I move off that line, it becomes AB to the 6 until I hit 3/4, and then the symbolic dynamics of this is this, and you see it's a repetition, or partly a repetition, because I'm periodic of period 4, and then I go past that and I change another letter, and if you now look at what's happening, I go there, 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 there. You see the 7 changes that take me from B to the 7 to A to the 7. Okay. So the first thing you have to figure out is not only is this net a boundary for symbolic dynamics, but as you walk along it, as you intersect other lines, you have the symbolic dynamics changing as well. Another thing we did was to recognize that when you have a rational point, there are many lines. If you have the angle rational, then the row, which is a multiple of the angle, it must be rational. And in this case, there are many lines of the net through the same point. And so what we showed was that in this pencil of curves that are the alternative higher values of the slope, then you maintained the same symbolic dynamics until you went up and hit this sort of neighboring curve up here. So there's a very tight organization as to when the symbolic dynamics changes in this case. And then we also looked at this net and we identified triple points. So we're trying to understand this net and what are the implications for the symbolic dynamics. And so these triple points are, we have a point in the middle and it belongs on a critical line, and then look at the neighbours above and below. So a triple point is when you see an intersection of one of the lines through it with the line through the two neighbours. And they come in two varieties, one either side, or this one, where there's one above and one below. And a lot of things that are going on here are driven by the continued fraction expansion of the rational angle. So one of them is 3/5 on the left, and the other one is 3/7 on the right. And so basically, we were able to classify the possibilities of these triple points based on the last two convergence of the rational theta. Okay, so I'm trying to argue with pictures now because it's actually a little bit finicky doing this, so I think this is the best way to go. And then you may say, well, we've sort of got to the end of the talk and you still haven't talked about this. And you'd be right. But, okay, so the rest of the talk and what the work on this is all about is basically realizing that the dynamics here is a composition of two things. Rays are rotated, and it's just knowing the angle of the ray is enough to give you the symbolic dynamics. Okay, so there's a motion of rotation here, and then there's the movement along a ray. So the dynamics is built of those two things. So Ligarius and Rains, so we're back to now looking at this. Ligarius and Rains showed that if you took a ray on the unit circle, took its image and then brought that back to the unit circle, you had a well-defined diffeomorphism of the circle, which also it was a diffeomorphism with bounded variation. This is enough to tell you two things: that there's a well-defined rotation number depending on the parameters you chose here. Remember, the parameters are A and B. And the bounded variation tells you that you are topologically conjugate to the model I've been talking about, rigid rotation with an angle R, A and B. So there's part of the dynamics that boils down to what I've been talking about. And for instance, here's just a picture from this paper of an example for particular values of A and B of this circle diffeomorphism. So I've just, this is 0, 1, 0, 1, and this is just the one-dimensional circle map. Okay. And now, Ligerius and Raines also showed that the number of periodic orbits you could have, you had to look at two things. You had to ask the question, are you periodic on the circle map, which just means that you come back in the same direction? And are you also periodic in coming back to the same point? So there's a count here of NS, which is the number of circle map periodic orbits, and there's a count NT, which is the number of map under the full map. Okay, and the basic point is that the map can only have one periodic orbit, and the other periodic orbits come from the circle map. And so the dynamics that we see here is for a rational rotation number. Okay, so now I'm drawing this space. I am going to see what are called resonance zones in, no, sorry, I should be. This is my parameter space, AB. There are going to be parameter combinations where this action will have a periodic orbit of the circle map. Okay, and so that means, and it'll be what's called a resonance zone. So in this whole region, in the AB space, every point that you take of this map, which has this rational rotation number, will be periodic under the circle map. In fact, what it'll be attracting to a periodic orbit on the circle map. So that's one type of motion you can have here. The other type of motion, and more interesting, is what's going to happen when you have an irrational. You look at an AB where the map has irrational rotation. Okay, so, and here is where we want to take everything I talked about for this map, the idea of critical orbits, and I want to take it here. So what's a critical orbit now? Well, the boundary of the symbolic dynamics is the y-axis. So let's ask for values of A and B such that you have an orbit which has a part that goes between, down here to up here, or it could also go from the positive y-axis back to it, or the negative y-axis back to it. But the more interesting one is the one that includes the negative y-axis and the positive y-axis. So this is an analogy of a critical orbit that I had over here, because obviously the symbolic dynamics changes either side of parameter space if I have these critical orbits. And so the game now is to ask ourselves, for what values in the parameter space AB can this map FAB have invariant curves? And Ligerius and Raines gave some examples. And so this one they call Bugs Bunny for obvious reasons. But they proved that if A was the fourth root of 2 and B was minus the fourth root of 2, then this map had this invariant curve, which is made up of bits of conics. Okay? It's basically the bits of the ellipses that the separate matrices with A being this value and B being this value would have if you'd just done a plot of the plane with that linear map. On the other hand, if you just start to put in nicer numbers that are not irrational, you get many suggestions that there is actually invariant curves as well. And from what I said before, remember, one invariant curve means you get a whole family of them. But it's fiendishly hard to try to prove that this is really true. So let me just end by saying what our program is with respect to understanding the dynamics here. So what we want to do is we want to take the AB space and we want to build a scaffold here of critical curves. So these are all the parameter combinations such that you can be guaranteed that for this parameter combination, there's an orbit that, for instance, takes you from the minus y axis up to the plus y axis. And we want to note its symbolic dynamics. And then we want to be able to see if we can understand, just as we had the net of straight lines that I called the fairy net for this circle map, we want to be able to understand, if you like, the bifurcation diagram for this. And then we want to ask ourselves, this has two parameters, A and B, but there's an underlying rotation map. So there's an underlying rotation angle, theta AB, and there's also an underlying, if you like, density parameter AB. So what I said here that rho is the partition for the symbolic dynamics, but in a sense it's also a density parameter that tells you how much time you spend in this interval compared to the rest. So explicitly, this parameter is write down this sequence that you're getting from this dynamics and write what proportion of A's you get, if you like. Okay. So we want to know, and this is a common dynamical thing, how much of the possible theta rho space is open to this map. Okay, because the original thing I did over here, rho and theta, I was able to choose whatever I wanted. And so I had, on my net here, I had a division of the whole theta rho space. And so I will cut to the chase, and I will just tell you that we have identified that the critical curves that we want in this space are all algebraic curves. The symbolic dynamics between hitting the two parts of the partition necessarily have to be palindromic. So the word has to be a palindrome. And you can write down what the algebraic curve is in this determinantal form, where the W1, W2 up to WT minus 1 are just A's and B's that you put in according to the palindromic word. The other thing that goes back to what I talked about earlier is that you ask yourself, the matrix words that you're getting on the critical words, they're all sending the y-axis to the y-axis. So all of these words share the eigenspace x equals 0. And if you go back to what I talked about trace maps, that's very significant because that tells you that these matrices are populating this surface of the Fricke-Vogt surface equal to 0. Okay, and so here is the program we're working on. Ask yourself, what is the allowed span of theta and rho in the dynamics of this Lagarius-Raynes map? And essentially what happens is that you are forced at the beginning to live in this triangle. So for instance, your rotation number can't be bigger than a half. And then, as is common in symbolic dynamics, you have to start pruning this because there are regions you can show that are disallowed here that you can't have in the Lagarius-Raynes map. And so the ultimate aim is to sort of explain what we call the Christmas tree. And this is a numerical look at what you get left with when you start cutting out all the theta rho combinations that are not available to you. So the blue, for instance, in the left is the image of basically each of these colors is the image of a quadrant, and it tells you the range of theta and rho you can get. And so this is a complex picture, and we're trying to prove it as much as we can. So thank you very much for your attention.